AP Calculus AB, this is homework 1.8. We're looking at vertical, horizontal asymptotes and how limits can be used to discover where those exist. For exercises 1 through 3, find the limit indicated. Explain what the result of the limit means about the graph of the given rational function. Well, the first thing we want to do, we want to try to evaluate this limit. And we can't in its current form because if you put -5 in, it's going to be undefined because you're going to be dividing by 0. Let's see if we can cancel this x plus 5 by factoring. The numerator factors into an x minus 3 and an x plus 2. So nothing cancels, which means this graph has a vertical asymptote at x equals -5. To answer the question about this limit, is the graph going to go to infinity or negative infinity as x approaches -5 from the right? Well, to determine that, we're going to use a little table. We're going to choose an x value to the right of -5, something close. Let's say let's see if we have a number line here. If we have -5, something close to -5 from the right would be like -4.9. And then if you plug that into this function, and I'm going to use the factored version because it's going to be a lot easier. If I put -4.9 into this first factor here, it's going to be negative minus 3. It's going to be negative. If I put -4.9 in here, it's also going to be negative. If I put a -4.9 into the bottom, well, that's going to be positive. If you divide two negatives, if you multiply two negatives and divide by a positive, that's going to be positive. Here's what that tells us. That this limit, as x approaches 5 from the right, is going to be positive infinity. And because that limit equals positive infinity, we know for sure that this function, which we don't have a name for this function, unfortunately, x squared minus 6 minus x over x plus 5 has a vertical asymptote at x equals -5. That's because this limit is equal to infinity. All right, let's try this next one. Maybe this one will factor and cancel. If things factor and cancel, if it's a canceling factor, that means there's a hole in the graph. If there's a non-canceling factor in the denominator, it means there's a vertical asymptote. So this is equivalent to the limit as x approaches -2 from the left of x minus 5 over, this denominator factors into an x plus 2 and an x minus 1. Nothing cancels, which means this graph is going to have a vertical asymptote at x equals -2. The question is this graph going to approach this vertical asymptote hold on a second, let me read the directions. Find the limit of each thing. Yeah. This is going to have two vertical asymptotes, one at -2 and one at x equals 1. But we are only concerned about the limit, so we're only concerned about that vertical asymptote. So we make a little table again. I'm going to pick a number to the left of -2, something real close, like a -2.1. And I am concerned with am I going to get a positive or negative answer for this? If I put a negative into the top, it's going to be negative. If I put a negative into this first factor at the bottom, it's going to be negative. If I put a negative into the second factor at the bottom, it's going to be negative. If you're multiplying or dividing three negatives, the answer is going to be negative. So this is going to negative infinity. So the conclusion we can draw from this, since x is approaching negative 2 from the left and the function's approaching negative infinity, it tells us that this function has a vertical asymptote at x equals negative 2. Number 3, let's see, this can be factored, the top and the bottom. Top factors into the sum of 2x and 3 and the difference of x and 1. The denominator factors into an x minus 2 and an x minus 1. Let's see, x minus 1's cancel. That means x equals 1 is a location of a hole. This is going to have a vertical asymptote at x equals 2. It's a non-canceling factor in the denominator. Using calculus, we can make a little table. To the right of 2, or to the left of 2, might be something like 1.9. And then we're going to plug that into this function. If I put a 1.9 in here, the top's going to be positive, the bottom's going to be negative. So that means that this is approaching negative infinity. So the conclusion we can make from this is that this function has a vertical asymptote at x equals 2. All right, moving on. Find each of the following limits at infinity. Now keep in mind, this is asking for the end behavior of the graph. Something else that describes end behavior of graphs are horizontal asymptotes. So in some cases, we are actually trying to find the location of horizontal asymptotes for this. Show your limit analysis, then explain why the results of this limit occurs with your graphical understanding of asymptotic behavior of irrational functions. Now before we even do the limit process, see if we can figure out what the answer is. X is approaching negative infinity. The leading coefficient in the numerator is negative 5x squared. The denominator is 2x squared. They're growing at the same rate. That means there's a horizontal asymptote at negative 5 over 2. So the answer to this question is negative 5 over 2. Let's use the process that we did in our notes, and this process will be obsolete once we learn L'Hopital's rule. We're going to divide every term in the numerator and denominator, the 6 terms, by x squared, because that's the biggest degree in the denominator. It's going to be 3x over x squared plus 2 over x squared minus 5x squared over x squared. Our denominator, 2x squared over x squared minus 3x over x squared minus 1 over x squared. Let's simplify as best we can. That's going to be the limit as x approaches negative infinity. It's going to be 3 over x plus 2 over x squared minus 5. Our denominator, it's going to be 2 minus 3 over x minus 1 over x squared. For the rest of these problems in the homework, I'm going to skip this first step and just go directly to this. If x is approaching infinity or negative infinity, each of these fractions in which you're dividing by an x or an x squared, and the top is just a number, each of these are going to go to 0. So that means we're going to have 0 plus 0 minus 5 over 2 minus 0 minus 0. It's negative 5 over 2. Exactly what we predicted at the beginning using our pre-calculus skills. It says show your limit analysis, which we did. Explain what the results of the limits has to do with the graph. Well, we can conclude from this that y equals negative 5 halves is a horizontal asymptote of the graph. Number 5, this is going to infinity. I think this answer is going to be 0. And the reason, once again, since x is going to infinity, it's asking for the horizontal asymptotes. The bottom is growing faster than the top. Therefore, this has the horizontal asymptote at y equals 0. That's pre-calc. Let's show the limit analysis of this. We're going to divide each term by the biggest degree of x from the denominator. 3x divided by x squared is going to be 3 over x. 5 divided by x squared is 5 over x squared. Denominator, 2x squared divided by x squared is 2, and minus 3x divided by x is 3 over x. This is going to approach 0, this is going to approach 0, this is going to approach 2, this is going to approach 0. So we get 0 plus 0 over 2 minus 0. That's going to be 0. Therefore, y equals 0 is a horizontal asymptote of the graph. Number 6, going to divide, well, let's go back to pre-calc real quick. This does not have a horizontal asymptote, which tells me this is going to be undefined. It doesn't have a horizontal asymptote because the top's growing faster than the bottom. But let's see what happens. We're going to divide each term by x to the biggest degree that's in the denominator. And that biggest degree is x to the first. So negative 2x squared divided by x is going to be a negative 2x. 5 divided by x is 5 over x. 3x divided by x is 3, and 2 divided by x is 2 over x. Things are going to get a little crazy here. This is going to approach 0, this is going to approach 0. That's easy. 3, you know what, I left this a sign mistake. This says minus here. Should be minus over here as well. Sorry. So 3 is going to approach 3 as x approaches negative infinity. Now up here, we're going to have negative 2, and we're going to put in negative infinity into this. It's going to be essentially like saying negative 2 times negative infinity. Negative times the negative is a positive. That would be the same as saying positive infinity. You divide that by 3, that's still positive infinity. As the graph goes left forever, it's going to continue to go up. That's what that means. This limit does not exist. Therefore, there is no horizontal asymptote. At least going left. There could be one going to the right. We didn't really evaluate that way. All right, on the flip side. Find each of the following limits at infinity. Explain how you arrived at your answer. In each case, this is asking for the end behavior of your graph. So for this one, I would say that the graph is going to look something like this, the end behavior. That's because we have an odd degree function, and we have a negative lead coefficient. So as we go left, it's going to go up. So I'm going to say this is infinity, and my reason is going to be the degree is even, I'm sorry, the degree is odd, and lead coefficient I before E except after C. I think I had it right the first time. That does not look right. Here's what I'll do about that. And lead coef is negative. So the graph rises to the left. Good enough. Number 8, this is a negative x. If you cube this x, it's x cubed. You would have a negative x times an x cubed. That would make this leading term negative x to the 4th. So I'm going to say this is going to negative infinity. That's because the end behavior of the graph is going to be like so, just like a quadratic that has a vertical reflection. The degree is even with negative lead coefficient. So the graph falls to the right. Number 9, this is exponential. We'd like to have our base to be bigger than 1, which it is. This is a horizontal reflection. There's no vertical reflection, so that means that this graph is above the horizontal asymptote and that it's growing towards it. And this horizontal asymptote is y equals -2 because the graph was shifted down 2. So as this graph goes to the right, it's going to get closer to the horizontal asymptote of -2. Explain your reasoning. You could simply say, since there's no vertical reflection, the graph is above the horizontal asymptote. And since there's a horizontal reflection, the graph is growing towards the horizontal asymptote. I'm not going to write all that. You don't need to either. Number 10, I would like to rewrite this so the base is bigger than 1, and that's going to change the sign of the exponent. This negative tells us the graph is below the horizontal asymptote, and because this is a positive coefficient for x, it's going to grow away from the horizontal asymptote. So it's going to be like this. So the horizontal asymptote is at y equals 3, because this translates the graph up 3. As we go left, it's growing towards it. So we are saying that this is going to be equal to 3. All right, 11 and 12. These are by far the two hardest. Find each of the following limits at infinity. What do the results tell you about the existence of a horizontal asymptote? We're going to do these like we did 1 through 7, but there's a little bit of a catch because we're going to be dividing by the biggest degree in the denominator, which appears to be an x squared, but it's really the square root of x squared. And the square root of x squared is going to be a negative x, and that's because we are told x is less than 0. We're told that here when it says x is going to negative infinity. So we're going to take this limit. We're going to divide every term by a negative x. And if that term is inside a radical, well, let's do the outside radicals first. So we have 2x divided by negative x. We have 1 divided by negative x. The denominator is inside of a radical. So if I'm going to divide that by negative x and it's inside the radical, I'm really dividing it by an x squared inside the radical. Let's simplify. I'm going to have negative 2 minus 1 over x, and then I'm going to have the square root of the difference of 1 and 1 over x. To evaluate this limit, since x is approaching negative infinity, if the fraction is 1 over x, that's going to approach 0. So we're going to have negative 2 minus 0 over the square root of 1 minus 0. That's going to be negative 2 over the square root of 1. That's going to be negative 2. What do the results tell you about the existence of a horizontal asymptote? Well, as x goes left forever, this is getting closer to negative 2. So we can conclude from that that this function has a horizontal asymptote. Y equals negative 2. All right, number 12 is very similar. This time we're approaching positive infinity. So if x squared, if you take its square root, that's just going to be x, and that's because here x is bigger than 0. It's bigger than 0 because we're going to infinity. So we're going to take this limit. We're going to divide the terms on the top by x, and the terms on the bottom also by x, but it's going to be in the form of the square root of x squared. And since this radical is already here, it's going to be 2x squared divided by x squared, and a minus 3 divided by x squared. Simplify this, we're going to get negative 2x plus 1. Denominator is going to be the square root of the difference of 2 and 3 over x squared. This limit's going to approach 0. This is going to approach 1. This is going to approach the square root of 2. And this is going to approach negative infinity eventually. So I have negative 2 times infinity plus 1 over the square root of 2 minus 0. That's going to be negative infinity. I think that you would agree, if you take negative 2 times infinity, it just changes the sign, so it's negative infinity. Add 1 to it, it's still going to go to negative infinity. Divide that by the square root of 2, and it's still going to go to negative infinity. Our conclusion from this is there is no horizontal asymptote. Minimally, there's no horizontal asymptote as you go to the right, because as you go to the right, it's going down forever. All right.